Yeah, let's wait for 2 more minutes for Professor Sherman Chow. No, no, you don't need to. You don't need to. I will anyway start in 35. Okay. Okay. So, hello, hello. Uh, yeah. So now we have Professor Sherman here, so we can start. The most important person like in the audience. So, uh, okay. First of all, thank you all for coming to today's talk. It's my pleasure to introduce our speaker, Mr. Youlong Ding. And Youlong holds a bachelor's degree from Shenzhen University, and he's currently a master student at the Hebrew University of Jerusalem, advised by Professor Ilan Komagowski. And his research interests span cryptography, differential privacy, and machine learning. One particularly interesting thing I found on his resume is that he beyond cryptography, he publishes like consistently at top tier machine learning conferences like Triple AI and NeuralRiffs and ICML, etc. Today he'll introduce his new paper admitted to stock this year. It's a paper on NC1 computable PRF from the assumption of a learning parity with noise. To be honest, I didn't expect to see a stock paper on such a fundamental or well-studied notion like a PRF. But yeah, that means this result at least is very impressive to me, and even more impressive, like he obtained such a result in his pursuit of a master degree. So yeah, with that, like Youlong, the stage is yours.
Okay, thanks for the introduction. I'm Youlong Ding. Today I'm going to present our recent work on new constructions of pseudorandom functions from LPN. This is joint work with Ayush Shan and my advisor Ilan Komagowski. So pseudorandom functions is a very fundamental primitive in cryptography. It has applications in almost everywhere. Informally speaking, a PRF is a keyed function with the property that for a randomly chosen key, the induced function is indistinguishable from a random function. In more detail, in a PRF game, an efficient adversary is given oracle access to a PRF for a random key. He can make queries to receive output, but he cannot distinguish whether he is interacting with a PRF or a truly random function. And now I'll introduce some variants of PRFs that will be relevant to this work. First, strong PRFs or simply PRFs, where the adversary can make adaptive queries, but still he cannot distinguish it from a random function. Weak PRFs, where the adversary can no longer make queries, he is only given input-output pairs for random input. And encoded input PRFs, or EIPRFs for short, where the input domain of the PRF is restricted to an efficiently samplable subset of all binary strings of length k. So as you can see, weak PRFs and EIPRFs are strictly weaker primitives than PRFs, but fortunately they are still sufficient for many applications in symmetric key crypto systems. And in this work, we'll also be interested in a special algebraic property called key homomorphic PRFs. So roughly speaking, if we take the addition of the outputs, then the result is equal to take the addition on the key. I'm a little bit abusing notation here because it doesn't need to be an add operation. It just can be arbitrary group operation in the underlying group. But for simplicity and throughout this paper, we'll use this add notation. And KHPRFs have many applications in symmetric crypto for key rotation and updatable encryption. Unfortunately, we don't know how to construct KHPFs without relying on random oracle model. What we can achieve in Plan model is a relaxed version called approximate KHPFs, where a small additive error delta is allowed. Fortunately, this relaxed version is still sufficient for many applications. So how do we actually construct PIFs? Well, it is known that the existence of PIFs is equivalent to the existence of one-way functions. And you can also imagine that if we perform overly complex computation on the input, then the output will likely to be pseudorandom. So what's really interesting or exciting is to try to build low complexity PIFs. And understanding such low complexity PIFs is very fruitful. It has broad impact beyond just efficiency metric in crypto systems. I've listed some applications in theoretical computer science here. Among many complexity measures, in the context of PIFs, arguably the most important aspect is parallel complexity, or the circuit depth. That is, if we allow parallel computation, what is the minimal time required to evaluate PIF? And I'll introduce a notation in C1 which denotes poly-size low-depth circuit with constant fine and/or and NOT gates. So it is crucial, for example, in the application of multi-party computation, the depth directly affects the number of communication rounds of your MPC protocol. And it's worth noting that we know how to construct PIFs in NC1, which is just low depths from many standard assumptions like DDH, factoring, K-linear, and LWE, but not from LPN. So next I'll introduce another primitive called block ciphers, which you might heard a lot in practice. So block ciphers can be viewed as a practical construction of PIFs, or strictly speaking, it's pseudorandom permutations. And examples can include AES. The design of block ciphers typically follows the SPN paradigm. SPN stands for Substitution Permutation Network, which dates back to Youlong. So an SPN typically looks like this. In each iteration, we have a nonlinear operation called SBox to confuse input, and then apply a linear operation to diffuse compute. Finally, we XOR the results with a round key, and this process is repeated many times to obtain output. So, and this heuristic gives us super efficient construction of practical PIs, which is block ciphers. But the problem is we are quite far from understanding its security. In particular, the construction of block ciphers lack a security reduction from well-established assumptions like DDH or factoring, or what was mentioned before. So there is a significant gap between what we do in practice and what we implement what we do in theory and what we implement in practice. This raises a long-term important question, which is, can we bridge the gap between theoretical PIs and their practical counterparts? And now I'll introduce the main assumption we're going to use in this work, which is learning parity with noise. So LPN states that samples of the form which inner products with A and S plus a sparse error E is random even given A. So we have the following procedure. You first sample A from matrix A of shape n times m from some distribution C. And for now, you can think of A being random. And then we sample a secret vector S. We multiply S by A and add an error vector E, which follows a Bernoulli distribution with parameter mu, meaning that it's equal 1 with probability mu and 0 otherwise. There are three parameters, which is the dimension n, number of samples m, and noise level mu. So if mu equals 0.5, then this is completely random, right? Because each EI is simply a random bit, no matter what S times A is. And the magic stuff here is if we set mu to be a fairly small value, say 0.001, then this error vector is sparse, but it's still efficient to render the output pseudo-random.
So your C is not just the pool, right? C can be arbitrary field, finite field.
Yes, C is, you can think of C as the algorithm that will output a matrix of the shape n times m. And for in standard LPN, C just outputs a random matrix. I'll talk about more in the next slide. Next slide.
Elements of A, are they also
Oh,
1 values?
Yes, they're also in.
So all your arithmetic are like modulo 2.
Yeah. It was noting that our construction can be extended to large field FP, but it's not likely to be in NC1. And now we'll introduce some variants of LPN that will be used in this work. Firstly, the standard LPN, where the C just outputs a random matrix. And a very popular variant of LPN is called sparse LPN. The public coefficient matrix is now a column sparse matrix. Each column will have exactly, say, t number of ones. And this assumption, this variant of LPN is well established and have been used for over decades. And we'll also introduce a new assumption called seeded LPN, where the Pauli matrix follows certain n-wise independent matrix. So by n-wise independent, it implies if we only look at any n columns of this A, it will be random, but the joint distribution of them is not.
So the second one is the one that I usually use to construct IO. The spark one.
I don't remember.
Okay.
I guess that yeah, I use sparse LPN a lot. Okay, so here are some reasons to motivate construction of PIS from LPN. Firstly, LPN is plausible post-quantum secure. We are not aware of any quantum attack against LPN, and arguably they are more conservative than LWE. Second, LPN is natively defined over binary field, which makes it suitable for hardware-efficient implementations. And recall that the practical construction block ciphers also have computation over binary field for efficiency reasons. We already know how to construct PIs from LPN, but it's not in the log depth. It's almost, but not. And they construct PIs through some generic transformation from PRG to PIF. So this epsilon overhead is somehow inherent in this approach. In the context of weak PIFs, a recent work constructs weak PIFs in NC0 module, which is contained in NC1, but they rely on a new variant of LPN called variable density LPN, and they conjecture it is secure. So this raises an important question, which is, are there log depth PIs based on LPN? So here are our results. We construct weak PRFs in NC1 that are computable by a circuit with log depths from standard LPN. And result 2 is an encoded input PRFs in NC1 from sparse LPN. In more detail, if you're interested in the sparse parameter, then any t that is subpolynomial in N will subsurface. That is, the sparsity parameter t doesn't need to be super small like constant or slightly super constant. This matrix only needs to be slightly sparse. And in the input encoding can be computed in NC1 plus epsilon. So if taking that into account, it implies a PFs in NC1 plus epsilon from sparse LPN. I know that I don't think this epsilon is inherent in each approach. Maybe in the future we can shave off this epsilon, and we'll talk about more on this later. Finally, we construct PFs in NC1 from CD LPN. It's worth noting that all our constructions are key homomorphic, and all our constructions nicely fits into the SPN paradigm that's followed by all modern block ciphers. So some remarks on our results. Our LPN parameter region is not known to imply PKE, which means that We are not using any heavy hammers, and our construction is non-trivial. And as I mentioned, the previous NC1 cumulative LPN that rely on factoring or DDH, LWE, they all imply public key encryption. And if you are interested in the concurrent security, we can achieve a slightly superpolynomial in NT and epsilon. That is, any adversary that has slightly superpolynomial running time, making slightly superpolynomial queries, can have advantage at most 1 over a slightly superpolynomial.
Well, I have a few questions. So, your sort of result is from CD LPN. Previously, there are extractions from VD LPN.
Yeah.
Both of them are like variants. So why, how do you compare them? Or are you feeling that your assumption is weaker than theirs?
VD LPN only gives us a weak PIF. Here we construct a strong PIFs, and our PIFs, and as I written here, are all key homomorphic.
I see. So your point is, even though you are also using some variant of LPN, this is the only variant known to imply standard PRF, not any something like a wicked.
Yeah.
Okay. Also, your thing in result 2, you can remove epsilon. In your paper, you already removed it.
Oh no. As we have some, it has some potential to be removed. So this is not something like the inherent limitation.
So then your result 2, the statement of the result 2 doesn't have epsilon inside.
Yeah, because it's EIPFs. The inputs, the given inputs are already in the encoded form.
I see. Also, can you explain something on your construction fits into SPN paradigm? I don't understand this. What do you mean by fits into?
So the SPN paradigm is an iterative process of 3 operations. That's we first apply a nonlinear S-box and a linear diffusion and XOR with and so all construction can be represented in this syntax. So are you saying you want to replace S by your construction, or just your construction itself looks like Yeah, just looks like this. Okay. And we'll talk about more on this later. Okay, so before presenting on construction, and I want to briefly give you some intuition that's why it's difficult to construct PIs from LPN. As I mentioned above, NC1 computer PIs from almost, if not almost all standard assumptions, but not from LPN. So PIF, and the starting point is in LPN we have a secret vector S, and we can use it to serve as a secret key. And we have also a random coefficient A, and in context of weak PIF, we can use A to serve as the input, and then the sample will serve as output of PIF. So what's the problem? The problem is, so the random function is a function, which is a mathematical object. That means the output should be deterministic. Well, this learning with parity noise has some randomized nature, because for each sample we need to sample a randomized area E. So to construct a PIF from LPN, we need to somehow turn a probabilistic procedure into a deterministic procedure. This is also referred as de-randomization. As it turns out, de-randomization for LPN is very difficult. Let's review how we do the de-randomization for LWE. And recall that LWE have the similar syntax as LPN. Well, the difference is that all the arithmetic are performed over ZP, and the error is some small value. So an example is in LPN the error is very sparse. If there are 4 entries, only one of them is non-zero. But in LWE, the error is not sparse at all. We only guarantee that it has small value in each entry. And if the error has small values, we can easily get rid of it by rounding. So here's a construction of weak PS from LWE. We take inner product between S and X and rounding it to 2. And this operation means that for all the values that are less than p over 2, we output 0, and for all the values greater than p over 2, we output 1. The security proof proceeds as follows. Because E is a small value, then if we adding the noise into this inner product, it will give us the same value with high probability, and then by LWE, this S times X plus E is uniform, and if we're rounding a uniform value, the output is just a uniform bit. So this rounding technique breaks down completely for LPN because, like I mentioned before, the error is not small but only sparse. And it's not clear how to rounding away a sparse error. So now I'll present our construction in step by step. The start point, here I'm going to present the first starting point. And we have LPN parameter n and mu, and we take mu to be some power of 2. And we have secret keys, which is a bunch of vectors on input A, or A should be a vector, there's a typo. And what we want is take the inner product between AS and plus an error. We need error here, and how about we generate error by extracting it from the secret keys? So we take the inner product of A to other secret key F's to get R. And we use this error bits to sample a Bernoulli random bit. How to do it? Well, the most straightforward way to sample a bias bit from uniform bits is just take the multiplication. And we take the mu, and mu happens to be a power of 2, so we only need to multiply these error bits. And I claim that if R is random, then the output of S follows exactly as the Bernoulli distribution with parameter mu. Then it is a secure weak PIF only if the number of queries is bounded, like say O of NL. Why? Because we have an NL bits of secrecy, and it can only provide us NL bits of randomness. We can formally argue this by using relative hash lemma, which basically states that if A has columns like n times L, then the extracted R is statistically close to a uniform U. And this analysis turns out to be tight, because if the number of queries is larger than NL, we can attack in the following way. We observe that the output of this function can be represented by a polynomial where variables are each bit of a secret key. So what you'll do is just linearize this polynomial and do Gaussian elimination to recover the variables, and then we can distinguish it from random. So here the problem is that R can no longer be argued to be pseudorandom if the number of queries is unbounded. So maybe the midpoint is, what if we sample L Bernoulli bits and add them to add them when we compute this R. Then
So first question is if our bits
you mean this slide?
who R1, R2, and so on.
I think R1, they are like bits of R.
Yeah, and then if you multiply by 0 and the whole thing 0. Then if you have 1 0, then the whole thing will be 0.
Oh, yeah. If one bit of R is 0,
Yeah.
then the whole thing
will become 0.
becomes 0.
Yeah.
So it's supposed to be 0 with some high probability by the definition of the bit.
Yeah, it's a bias bit, only with very small probability mu, it equals 1.
Okay, so you would compute some the corresponding probability mu from this.
Yeah, because I take mu to be 2 minus 2 to the minus L. It happens to be a power of 2.
Okay. I'm not familiar with the visual design, so I also understand that it's still the starting point, but what is the improvement about this line? What's new about which part of the component is so starting to create on the own? Which part is new? Or the new version calculate?
I think he's asking, is this construction known or it's your result? One of your results. This
Oh, it's not known. So it's
It's
kind
not known.
yeah, it's kind of trivial.
Yeah, so this one is still the starting point.
Yeah, yeah, yeah.
Cool.
I think that's why it has a starting point.
Yeah.
and problem. I think the story is that if you put a deep query bound big O and L, then it's probably easy with the trivial construction. I guess some randomness extractor.
Yes, yes. Okay, so the midpoint is, what if we sample random Bernoulli bits and inject them when we compute R? Then the R can be argued to be pseudorandom under LPN for unbounded number of queries. Now it is secure, but the problem is, again, it's no longer a function because we are doing some randomized procedure, but the function requires deterministic. So how do we solve this problem? Well, basically, we just recurse and we do nothing but just recursion. So you see that we generate a bit of random Bernoulli bits here, and we require the red bits. What we do is, whenever we require a red error bit, we invoke this procedure to generate it. It might seem very abstract, and I'll be more precise in a few slides. Here I just give you some basic idea what's going on. So whenever I require a Bernoulli bit, I take the inner product between A and another set of secret keys to derive Bernoulli bits provided. So as you can see, this sub-procedure also requires red Bernoulli bits. So we keep recursing by invoking this procedure again and again until reach to some point where we just take the inner products between A and S, and there is no Bernoulli noise injected. So if we unroll all the recursion structure, and the picture will something like this. This is a top layer. We need L bits of Bernoulli noise. Then we invoke this procedure L times to provide L Bernoulli bits and keep recursion. So the structure will, like a tree, have fan out of air. If we do recursion for depth tau, then the size of a tree will be L to the tau. So something very crazy going on here because the size will grow like exponentially large. But as long as this tau is not very large, the size can still be polynomial.
So I think I don't see the stop condition. Where will you stop? What's the first place you do not require this Bernoulli bit?
And the bottom layer, we just take the product at the base of the recursion. We only take the products between A and S, and we use that to generate Bernoulli bits for the top layer. So I'll be more precise in next field. So here is a precise description of what's going on.
Basically, as long as I know L, I can decide when to stop. That's your story.
Yeah, I keep recursion for the depth of tau.
And until I reach the desired depth.
Yeah.
At that level, I'll just say, okay, I do not add E anymore.
Yeah. So here is a precise description. We have secret key, and as for each layer, we have different colors denotes different secret key for different layer. So there is exponential growth here. And on input A, as the base layer, say alpha equals tau, I just take the inner product between A and S. And then I use this R to sample Bernoulli bits E. So S is shrinking, right? If the input has a length L to the tau, then the output of S will be L to the tau minus 1. Because for each length error block, I use S to map into one Bernoulli bit. So the set length will be shrinked by factor of L. And for the intermediate layers, I compute R by using the arrow derived from the previous layer. And I keep repeating this process until I reach the root of the tree, which is just inner product between AS. So here is an illustration of the computation. I compress the layers to group them into a vector. So the computation lacks a straight line, while the base layer is just inner product between A and S. And we apply the S function and other results to the inner product of the previous layer. We keep repeating this process until we reach the top layer, which is just inner product of A and S.
What is at your instruction?
Now S is the secret key.
No, you have the box.
Oh.
What's the analog in your construction?
Oh, this S is a Bernoulli sample function that's defined here. Just take the product of error bits.
Okay, I see. Okay, good.
So here is the observation. As you can see, all the inner products can be done in parallel. There is no inherent sequentiality. So what we do next is we compute all these inner products first and then start the recursion. So as you can see, what we do is compute this Y first, which is the inner product of A. And S is a concatenation of all the small s. And for each iteration, if it's a base layer, then I is equal to Y. And if it's intermediate layer, I is Y plus a small arrow.
All right. I think one invocation of S just give you a single bit, right?
Yes.
But if you go to the previous page, I think you need for each level you need L.
Yeah, L to the power of alpha.
Or alpha bits. However,
so you can think of this S is concatenation of all the S, all the small vector S. So all these inner products I do it all together.
It's simple. Look at it just previous. Yeah.
Okay.
Look at the definition for alpha smaller than tall case. You need E1, E2, E3 all the way to E sub L to the alpha, right? However, your next line just define E. This E is a single bit, right?
Well, this E is not single bit. It's a vector. The L to the alpha.
So your F just output a single bit. Right?
Yeah, I'm extending S to a long input that basically treats each length error block separately and outputs a vector.
Oh, so R parenthesis alpha is how long is it?
R is R alpha is
L to the power
alpha. Yes. So I get a shrinkage in the length.
Okay. Yeah.
And now, if we set in this tau to be log n over log L, then the Q depth, the key size, which is L to the tau, is polar in N. And the evaluation depth, which is log n is the cost to compute Y, which is the first vector matrix product multiplication. And for each iteration tau, we need to compute S. S is the product of L bits, which takes depth log L. So the total depth is tau times log L. And if we choose parameter in this way, this term will also be log n. And the key homomorphism property is straightforward because the output has it's exactly the form for key homomorphism. Okay, that's our construction, and what remains to do is to argue its security before we prove its I'll draw connection to the SPN stuff now. And this figure you might already familiar, which is very similar to what I present in the SPN. So actually, an alternative view to view this construction is a block cipher from LPN with key homomorphism, where the round key is the key schedule procedure is take the inner product of A and S to derive the round key, which are used to XOR with the output of linear. And in our weak PF construction, this linear function is actually an identity, but for our strong PF construction that will be presented later, this linear is a non-trivial linear transformation, which is not identical. And what's more interesting is this S-box. And recall that in modern block ciphers, this S-box is implemented like, for example, in AES, the S-box take input X and output its inverse. And in MIMAC, we take the cubic of X. And I don't understand what does it mean to take the inverse of a binary vector. What I'm going to do here is simply sample Bernoulli noise, which is a multiplication of L bits. So now let's dive into the security proof of our weak PF construction. And here a disclaimer that what I will describe later will be informal, and please refer to the paper for formal treatment. So here denotes this weak PF construction by G. I'm arguing like for one input A and a secret key. Note that this is not a PF game. I'm only arguing for one input A and secret key. Condition on the event that there exists alpha in tau, that there exists certain layer, such as S alpha, and S alpha denotes the S box as layer alpha. If S alpha outputs 0, then the output of G is kind of independent of the value at the bottom layer. Why is that? Because let's say if the S box in layer 1 output 0, then what feeds into the layer 0 is just inner product of A and S. It doesn't depend on what the base layer is. So again, this description is not very formal. It just gives you some intuition what's happening here. And I claim that the probability of there exists some layer alpha, such as the S box at alpha outputs 0, happens almost all the time. And this epsilon is some negligible value. This implies that the output of G almost always independent of the value at the base layer. Then what I'm going to do is replace the base layer tau by a fresh random R. This variance L denotes G.
Your base layer meaning layer tau.
Yeah. So for each input A, I'll sample a fresh random R at the base layer and evaluate the PF. So this tilde G is no longer an assumption, or is no longer a function because it's not deterministic. And then I claim that the adversary cannot distinguish between G and G tilde. Why is that? Because as I claimed above, the output of G is almost always independent of base layer, so we are free to replace the base layer by any other values. Then the lemma 2 is the adversary cannot distinguish between tilde tau and R, where R is a truly random function. Then by triangle equality implies that the adversary cannot distinguish between our weak PFG and a truly random function R. Now I'll go into more details of the claim of the three claims I need to prove. Claim 1 is that for one input alpha, or for one input A and secret key S, the probability of there exists one layer, such as S box at that layer output 0, happens almost every time. in words, the output of PIF is independent of the value at the base layer tau.
Can you remind me of your probability space? Your probability is taken over what?
Taking over the random inputs A and secret key S. But
You said for fixed alpha and beta.
The more formal treatment is we sample a random A and alpha, then the probability of this happens. So it is 1 minus
Over the
negative
random sampling of A and
S.
Then this is even about the existence of alpha.
Yeah. How do you prove it? First, we fix any layer alpha, and the S balls at layer alpha output 0 if and only if the output of its preceding layer doesn't contain an air length block that's O1. So here is the input to the S box, which I divide them into air bits, and there are L to the alpha blocks in total, and I feed them to the S box at layer alpha and get output. So the outputs will only be 1 if and only if the input air bits are all 1s.
This is just union boundary.
Yeah. And for each LB block that's denoted by V, I claim that V is uniformly distributed. Why is that? Recall that V is computed by A times S plus arrow E, and S is full rank because S has is a random matrix, and a random tall and skinny matrix is full rank almost all the time. And recall that A is random, so the product of a random value by a full rank matrix is still random. And this implies that if we take an offset E, the result is still uniform distributed. I'm a little bit cheating here because it actually requires that E is independent of alpha. If E dependent on alpha, it is no longer uniform random. But you can believe that, or one can show that this E is indeed independent of alpha, independent of A. So the probability, because V is uniformly distributed, the probability of E equals O1 string is just 2 to the minus L. And then I take union bound for all the blocks, which incur a multiplicative factor of L to the alpha, because there are L to alpha blocks in total. So now I consider for all the alpha in tau, the probability of for all alpha, the S alpha doesn't output 0 is something like this stuff to the power of tau. And this green event is the complement of this red event, which I want to know the probability. Okay, let's finish the proof of claim 1. And now the lemma 1 is the adversary cannot distinguish between G and G tilde. From claim 1, we already know that for one input A and the secret key S, they will have the same value except with epsilon probability. Then what I do is just take a union bound over all inputs. For secret key and the inputs A1, A2 to the A poly n, because the adversary can query the PIF at most poly n queries. I take union bound over all these queries. Then the event that these two functions give me the same output will happen except with probability epsilon times poly n, which is still negligible, let's say epsilon prime. So this concludes the proof of lemma 1. And now I'll conclude lemma 2, which is a security proof for the this variance tilde G. The proof proceeds as follows. Because we are sampled the base layer random, and S is a Bernoulli sampler, so this will imply that the E derived by this random value follows Bernoulli distribution. Then under LPN, we have the inner product of AS plus its arrow is random. So we move from a random R at layer tau to a random R at layer tau minus 1. We keep repeating these arguments tau times, finally reach at the output is random. This finished the proof. So to briefly review what's going on, we first prove some independence property of our construction, which implies that our construction will be indistinguishable from its noisy variant. This argument is information theoretic. There is no cryptography assumption. And then we use LPN assumption to prove that this noisy variant is indistinguishable from a truly random function. Then we prove that our construction is indistinguishable from random. It's worth noting that this security proof is similar and inspired by a recent work, HIM 20, and that was introduced to build KHPS from LWE with the polynomial modules. Now let's try to use a similar idea to build a strong PS from LPN. So we sort of want to reuse what's going on, and namely we use the secret S for the secret key and the LPN samples as of output. But in the context of strong PFs, the coefficient A can no longer be the input because the input is adversarially and arbitrarily chosen by the attacker. So what we want is to generate a good coefficient AI from the arbitrary input xi, which is sort of like some input encoding. And by good, I mean it will enable a security proof under LPN. So we suggest two approaches. The first approach is to use a template from BLR 13 to build a strong PFs and use the exactly same recursion idea to provide the arrow bits. We are relying on sparse LPN. Recall that in sparse LPN, each column is sparse. As it turns out, we can generate this input encoding A in NC1 plus epsilon. This gives us a EIPFs in NC1 if we do not take the input encoding into account. The second approach is to use a n-wise independent AI. Namely, we encode each input as the output of a n-wise independent hash. Then we get a PFs in NC1. So let us dive into these two constructions in more detail. For our first approach, the starting point is from the templates from BLMR. And you don't need to understand this fully because it's just like we do similar things here. And again, we can argue this strong PFs is secure if the number of queries is bounded. Now what we do, and again, if we can sample random Bernoulli bits, then it can be proven to be secure, but no longer function. And what we do again is just recursion. Whenever we need a Bernoulli bit, we invoke itself to generate it. We make the same observation that all this matrix multiplication can all be done in parallel. So there's no inherent sequentiality in computing this matrix production. But there is an issue because when we compute the inner product between the vector matrix multiplication of E and A, the E is derived from the previous layer. So there is some sequentiality here. And this multiplication requires log n depth because E and A all have the dimension of n. And we have a sequentiality of tau. This will bring the total depth to tau times log n, which is no longer in log depth. And before we introduce a technique to solve this issue, I just quickly also mention that this is a Bloch cipher, can be viewed as a Bloch cipher from LPN with key homomorphism, where the key schedule is the multiplication of your secret key and the encoded input. And the linear function is just defined by this matrix AX. And AX is defined to be the matrix multiplication of A. Okay, now let me briefly describe how we solve this, solve the issue that mentioned before. So our goal is to, here is the abstractive problem. We want to sample a Bernoulli noise E. This E is a vector using some randomness R, then compute the multiplication of E and A. We want to perform this procedure in depth that is little o of log n. So an observation here is that the matrix A is sparse. Each column will only have t number of non-zero entries, which means that by computing the multiplication of E and A, each column of A will touch only t entries in E. So there are certain locality properties here. And we can do a lazy sampling as follows. If we're only interested in the first bits of E times A, we can sample t Bernoulli bits E1 to ET using R, then directly take the sum of these t bits. And I claim that the sum of these t Bernoulli bits will follow the exactly same distribution as we take the inner product between E and A.
What is T? T.
T is the sparsity of the A. Each column of A will have t number of ones.
The T is a fixed number, or for different columns is different.
Yeah, T is a parameter, a fixed value. So we can fix the issue. Now the total depth is only tau times log t. And as I mentioned, t is a subpolynomial in n. So the product of them is still in log n.
But if you replace E times A using E1 plus E2 over ET, the result is independent of A, right?
Yeah, it's independent of A. Here is a simplified version because we're only interested in the first bits of E times A. And this idea can be extended to have multiple input bits. What we do is just consider the dependency pattern. That's
that pattern depends on A. So
yeah.
Information of A.
Yeah. Here is a simplified version.
Oh, because it has some joint distribution.
Yeah. Now I return to this input encoding. And our goal is to on inputs of length k compute this matrix, the sparse matrix multiplication. Here is the illustration. And as I mentioned, this computation needs depth that's larger than log n. But fortunately, this computation doesn't depend on your secret key. So it can be done by public computation. That is what EIPI is for. Now we are not clear whether this production can be done in NC1, even for constant sparsity T. But as I claimed before, I said that it has the potential to be in NC1. And why can we hope that? And matrix multiplication is like a variation problem. And why can we hope to do this in low depths? The key observation here is that the A is fixed. A doesn't serve as your input to your matrix production algorithm. is just a parameter of your algorithm. They are fixed once they are chosen. This allows us to do arbitrary processing on A. And with this processing on A, what we're going to do is on input X, we select some matrix A based on each bit of Xi and take the multiplication with the help of some maybe hint, which is derived from processing. Hopefully it can be done in NC1, but now we are not clear how to do it. And what we show in the paper is another implication that if we know how to do this matrix multiplication in NC1 for a constant sparsity T, it shall imply that for any T that is superpolynomial in N, this matrix multiplication will be NC1. Which means that we can just let T to be any superpolynomial, and recall that T with superpolynomial corresponds to a more conservative sparse LPN. There is no need to use a constant T for the hope to compute it in NC1. Now I'll describe our final construction, which is PIS from seeded LPN. Our seeded LPN states that for a hash function NYS, let H be an NYS independent hash function that maps from ZP to P. And each column of this coefficient matrix will be generated by the bit decomposition of H of I. And we show that this assumption is secure against linear tests. An important observation about LPN assumption is like many existing attacks against LPN can be put into the framework of linear tests. So if we can show it is secure against linear tests, we can it implies that it is secure against these existing attacks. So here is our PF construction on input X in ZP. What we do is just compute the H of X, or there is a bit decomposition here, and then invoke the weak PFs with input A. The weak PF is what I shown before, the recursion idea. So the overall depth here is the depth of computing the hash and the depth of weak PF, which is in log n. The security is proved under this CDLP assumption. Now I'll briefly give you some intuition like why CDLP makes sense. How about we have an analog in the LWE region that's CDLWE. That is, for simplicity, just consider this matrix A is deterministic. Then the CDLWE or deterministic LWE states that we sample a random vector S and multiply it by the deterministic A and add an arrow vector. Then the output is indistinguishable from random. Here I'm going to show an attack. The offline phase, I do preprocessing on this deterministic A. I want to find a small x. Each entry of x is bounded by some value b, such that a times x is equal to 0. Then, on the online phase, given we are given a b, which is LWE sample, we compute the inner product between b and x. Recall that since a times x is equal to 0, so b times x will be exactly equal to e times x. Since both e and x are small, the output will be a small value, then we can break it. And similarly, we can do the same attack for the deterministic LWE. Here, we want to find a sparse x such that ax equals 0. And in the online phase, we compute b times x, which is the inner product of two sparse vectors, and multiplication and the inner product of two sparse matrices is equal to 0 with high probability, then we can also break. But I'm missing some points here because I'm only saying that I want to find x, but I didn't say whether this x exists or not. In LWE, one can show that such x always exists, let's say by some counting arguments. In more detail, by counting arguments, there always exists two different x that will map to the same value. So we just take the difference of these two different x. That will give you an x, which will be mapped to 0. However, in LPN, such x does not exist except with negligible probability, because if A is n-wise independence, then any n column will be linearly independent with high probability. So because they are independent, linear independent, there does not exist a sparse x that will gives you 0.
Wait, but A, you don't have randomness over A. A is fixed.
Yeah,
Then
determinist.
pick the good A to be A.
Let's say I just sample a random A and fix it, because a random A will likely to be have high rank. Then
this is something you don't want because it gives you a tag.
So this means a random A is good enough to defend the attack.
Then I also have a question like E times X is 0. Is it 0 with high probability?
Yeah, because it's a production of sparse vectors.
Or sparse X?
Yeah.
Oh, you just say sparse, but on the LW side, you don't require it to be sparse. X to be just some short.
Yeah, in LW, I require S to be short. So this means that LPN is very different to LWE. They have very different nature. What this slide shows is.
Okay.
So in that sense, we can propose new assumptions of LPN, where the matrix A is no uniform random but have some structure. As long as that structure doesn't allow this attack, then it very much makes sense.
Yeah.
Here are some open problems. So like I mentioned before, is this sparse selective matrix production in NC1? If it is, then our construction too will be a PIF in NC1. And as I mentioned before, we showed that CDRPN is secure against linear tests. And can we do further study to further justify its security? And can we argue exponential security of our constructions? Because our construction currently is only provably secure, or provably superpolynomially secure, but not exponentially secure. And can we argue the security for practically usable ciphers like AES or suitable modification of AES? Or alternatively, can we define efficient block ciphers with provable security? That's all for my talk. Thank you very much.
You let's give it a one more for questions. So maybe ask about the literature. So from LWE, we know NC1 computable PRF.
Yes.
I know that you mentioned the word bi-boil.
Yes.
But if I remember correctly, there's construction from the Grid Packer, the synthesizer construction.
Yes.
Is that one also NC1?
Yes. So BMLR can be think of as transforming that construction into a key homomorphic PIFs.
Oh, okay.
Both of them are
also toward key homomorphism.
Yeah.
Also, I think I can't memorize your result. Can you go to the page that summarize your result?
Okay.
So this week PRF construction introduced, it just rely on standard LPN.
Yes.
So you need the sparse assumption to get one.
To fix the issue here, let me quickly.
Maybe you can return back from
Yeah.
mode.
So here is an issue that we need to compute this E times A.
That dialog.
Okay. We need to multiply this E times A, and each of them has dimension n. If A is not sparse, we don't know how to do it in depth less than log n.
So your eventual, you need this first recover to convert your weak PR to a EI PR.
Yeah.
Okay, then you can go back to the page where you summarize here.
Okay.
Okay. So your result 2 make use of result 1. You get a EI PR even C1 from sparse LPN.
Yeah, result 2 use a similar idea in result 1.
Okay. Also, you know that there are some generic transformation from weak PR to standard PR as well. So,
Yeah, that's what causes an overhead. That is a super constant in depth.
that doesn't also sacrifice some security. For example, you're gonna make super polynomial assumptions if you want to do that conversion, or it's just a standard reduction polynomial time. However, you lose the depth.
Yeah, I think it's standard. Just lose the depth.
Okay. Also, I'm curious. As this sparse LPN, I think in your previous slide you mentioned that you mentioned the citation from the work by I think DIJ
Yeah.
Rachel and
Yeah.
Did that work just construction of IO? Not that one. Older. Okay, so
That one is like a memorable master purpose.
then you know that if sparse LPN imply IO.
No, I don't know. I suppose so.
I guess. Otherwise, you can use IO to convert a weak for function, weak PR to standard PR. Yeah. Yeah, but I think if I remember correctly, you can convert weak PR to standard PR using IO. Okay, never mind. So yeah, then that's this is a great topic. Thank you for sharing.
Okay.
Do you know any extra applications of CP the LPN? CP the LPN. You just propose this in this one. CP the LPN.
Oh, CDLP.
Yeah, CP the LPN. You propose it in this one to get this PRF, right?
Yeah.
So do you find like it can also imply other primitives beyond PRF?
So the CDLP is basically like we make assumptions with respect to the public matrix that has some certain structure, and there are already a bunch of lines that rely on the A has certain structure. Just here we require it to be NYS dependence, and in other works they require A to be some other structure. So like making assumptions of LP and rely on structure A is very useful in the literature.
Okay, sure. Yeah, then I think that's all question. Well, thank you. So let me stop